This is the sequel to finding the area in between curves. Alright, I wanted to do one more example that looked like this. The reason I wanted to do this one is because here we want to run into a little bit of trouble. Think about these rectangles that I've been asking you to draw. It's really skinny guys. Alright, doesn't seem like a problem. Doesn't seem like a problem. Oh boy. See what happened here? Now we have a new upper curve, right? Remember I always told you to do top minus bottom? But look, for some rectangles, the top is the red curve. But for other rectangles, the top is the green curve. Okay? Two ways to attack this. I'm going to show you both. All right, here's the first way. The first way is you just split it up into two separate integrals. All right, so what we'll do is we'll find, let me do some erasing. We'll find, sorry if I'm not drawing so straight. We'll find this area. And then we'll find this area. And then we'll add them together. And that should do the trick, right? That should give us the full area. All right, so that's technique number one. And then I'll show you technique number two. All right, so with technique number one, first things first, we know when we are trying to find the area in between curves, we're going to have to find points of intersection because that'll help us determine our limits of integration. All right, so hopefully you can see that both the red and the blue are going to go through 0, 0. Let's see, the red is the linear, so obviously when x is 0, 4 times x is still 0. So we know this is going to go through 0, 0. Oh, sorry, the other one too. The parabola, blue is the parabola. So when x is 0, 0 squared is 0.5 times 0 is still 0. Okay, so that point's obviously 0, 0. Let's look at this one. The straight horizontal one is 8. So we know that the y-coordinate here is going to be 8. All right, how about the x-coordinate? It looks like it might be 4. But let's see, is the parabola when x equals 4? Let's see, 4 squared is 16. Half of 16 is 8. Yeah, so 4, 8. That's a true intersection point. All right, how about this one? This one looks like it might be 2. All right, once again, we know the y-coordinate's 8. Let's plug in 2 to the linear. 4 times 2 is 8. Yeah, sure enough. Okay, so 2, 8 is that point right there. And I'll label this one as 0, 0. Okay, so technique number one. We're going to find this area right there. Okay, so that area, our limits of integration, we're going to make rectangles that go like this. So the limits of integration are going to be in terms of x, and it's going to go from 0 to 2. Okay, and then we do top minus bottom. So the top curve is the linear one, so that's 4x, minus the bottom one, which is our parabola, minus 0.5 x squared. Okay, so that's the first area. Now let's find the second area. Second area, the representative rectangles are going to look like this. Okay, so once again, they're going to be in terms of x. So we put in dx, and our limits are going to go from 2 to 4. Okay, and once again, we're going to do top minus bottom. The top curve is 8, and the bottom curve is the blue, 0.5 x squared. Okay, so we could evaluate this. I'm very confident you can do this on your own. I'll show you in a second how to do that on your calculator if you need to, but I know you can do that one on your own. It's pretty simple. Okay, so I'm going to leave that calculation up to you. What I really want to show you here is this other technique. Okay, so that's technique number one, where we split it up into two separate integrals. All right, here's technique number two. All right, so for technique number two, instead of making our rectangles like this, where we have different limits, different upper curves, instead, we're going to make our rectangles like this. See that? That way it's always in between the blue and the red. Okay, they have the same right side and the same left side. Okay, so what that means is each representative rectangle, now instead of having dx be its width, dy is its width. Okay, so we're going to be doing an integral with respect to y. Okay, so we're going to be summing up all the rectangles like this. So our limits of integration now are going to be the y-coordinates from 0 to 8. All right, so there's our new limits. All right, notice since we're integrating with respect to y, the limits are y-coordinates. Okay, and also if we were to put x's here, it'd be really hard to integrate, so we need to put y's there. Okay, So what we need to do is take these two functions that matter to us. Let's see, the blue one, the parabola, and the red one, the straight line. And instead of getting them in terms of x, we're going to get them in terms of y. Okay, so y equals 0.5 x squared. Now let's solve for x. So y, let's see, to get rid of that 0.5, so we have 2y equals x squared. And then we're going to take a square root. Okay, and really we need that plus or minus, right? But let's remember what the plus or minus does here to a square root function. The plus will give us this positive square root, and the minus will give us this negative. Since we're not using this piece over here, we can ignore the plus or minus. Okay. All right, so x equals the square root of 2y. All right, now let's try the straight line. So y equals 4x, so obviously x is going to equal 1/4 y. Okay, so here instead of top minus bottom, instead we're going to do right minus left. You know, once again, like we did last time, let's say that's 3.5 and 1.5. So we know that 3.5 minus 1.5 is 2, so we would know the width of this is 2. Okay, so we always want to do right minus left when we're doing integration with respect to y. Okay, when we're doing integration with respect to x, we do top minus bottom. So here when we're doing integration with respect to y, we're going to do right minus left. All right, so the right curve is our parabola. Our parabola is this guy. So square root of 2y minus our left curve, 1/4 y. Okay, and once again, this is an integral I'm very confident you can do, but actually I'm going to go over this two different ways, once on our calculator, and then once I'm going to show you how to do it analytically. All right, so let's go to the calculator. Okay, so here we're looking at the calculator, and I actually did it both ways. First is technique number 1. So first I'm taking a numeric integral of y2 minus y1. Check out what y2 and y1 are. So y2 is the straight line, and y1 is the parabola. Okay, so I'm taking the area in between the straight line and the parabola with respect to x, with the limits of integration from 0 to 2. And then to that I'm adding the integral y3. y3 is 8. 8 minus the parabola, so the area in between the horizontal line and the parabola with respect to x, going from 2 to 4. And notice I get 13.33333333, which I'm confident you could do without a calculator, but I just want to remind you the notation. So notation is numeric integral. Remember, you get there by doing math 9. Then I'm using the variables, but you don't really need to do that. You can type it in terms of x, just the regular way that we're used to. Remember where that is. You go vars for variables over to y vars, and then function, and that's where all those goodies are. All right, so it's the numeric integral, then the integrand, then what you're taking the integral with respect to, so it's dx, so it's x, and then the limits of integration are 0 and 2. Okay, so I just wanted to remind you that. All right, then here's how we did it with technique number 2. All right, technique number 2 required y's. However, my calculator doesn't really do y's. I have an x button. So anywhere there was a y, I used x. Okay, so the square root of 2y minus 1/4 y. I'm integrating technically in terms of y, but I have to type in x, and my limits now are 0 to 8. And notice I get the same thing. Well, sort of. It's a little bit off, right? But we shouldn't be concerned by that because our calculators are TI-84s. Even though they're pluses and silver editions, they still don't do calculus. Instead, what they do is they just draw a ton of rectangles. I don't actually know how many, but maybe like 100 rectangles. And they find the area of all those rectangles and then sum them up. Okay, so it's an extremely good approximation, but that doesn't do calculus, so it won't do it exact. If you do want to get an exact answer, even though this one's correct to all those decimal places, let me show you the work for that. So here's the work for technique number 2. Okay, I'm not going to go through it step by step. I expect that you'd be able to follow it, but if you do have any questions on anything from this video, please write it down, bring it to class, and if you want to spend some more time with this work, you should pause the video. See you tomorrow.